Okay, so good afternoon. Welcome. So let's start. Okay, so since we are running late, let's start. I think I've already done this. So most of you have sent it. I think you have worked out, and then some of you, or most of you have sent it by email. That's good. Those who are still working or still you can cross verify. This should be like this group multiple table. Hope it is visible. Um, so as I said, there should be elements present in the CPE point group on the top and the first row on the left column, and then you just take the product of it. Then write the result. So you take the molecule ammonia or phosphine, you label it, say HA, HB, HB, and then let's see. Question is where is sigma V plane? So sigma V plane, you can say this is sigma V prime. To place it here, maybe consider as double prime, and if you take it this atom, so just consider sigma V triple prime. So just placing mirror something like this. So from that you can make it out different things. So this is, I hope you have done it by rotating the molecule, taking the plane, and then identifying it. It's a tedious job, but still it's worth making it. So you just practice it if you have not done it. There is easier way also of performing it. That's by matrix multiplication method. You can one can write the operations or all these operations in the terms of a matrix. Once we have the matrix for each element, for E, C3, C32, sigma V prime, double prime, triple prime, when we write in the matrix form, then just taking product of two matrices is much easier, right? So that then you give the third, it will give you a product, and that can be mapped with what is the symmetry element of that matrix, resulting matrix. So much easier way is using the matrix. That will come shortly. I think last class I started with group. Yeah. So group is a collection of elements satisfying four characteristics. Um, so note it down, please. If you have not, please note it down. Groups are group. It's a collection of elements which satisfy four characteristics. One is what? First is combination of any two elements in a group will result in another element which would be part of that group. That is um, combination of any two elements. So it's also part of that group. So if you combine any two, A, B, it can give a C. Then C also has to be in that part of that group. If you have, say, CD, use E, um, or better example could be BC equal to D. If you take combination another two combination, say B into C if you're taking, and it results in say it results in D. So D is also part of that group. So that's what it means. So if you combine it, we get a new one, and that is also part of the group. Okay, so that's what it means. And this is first characteristics. If special, there is something called abelian group. So what it means is if you take a combination of AB if it results in just same as BA, then this group is called as abelian group. Okay, so not all groups are abelian group. Only certain groups are abelian. So if you take A into B and you get some product, right? And if you take B into A and both, it should give the same product. So meaning, say AB is giving C, BA also should give C. So that is called as abelian group. Okay, so good example is H2O. What C2B is a abelian group. Okay, so C2B is a abelian group, whereas C3B is not a abelian group. Okay, so this is outcome of the first property. Erase this. So second is every group has one element which commutes with every other element. So this is a group has an element which commutes with every other element. So commute means it just mixes it and then gives the same thing. So identity is the element which commutes with every other element. So E into, so for example, E into C2 will again give C2. So E into sigma V prime will become sigma V prime. So it results in same element, right? It gives the same element. So that's what it's called as commute. So E is present in every group. So that commutes with every other element in the group. So that's second property. Third is associative law holds good. Is valid, I can say. Say you have a group with four elements. If you take the combination of four elements, say A, B, C, D, and if you combine this in any fashion, say A, B, you take the product of AB and then multiply with CD, or you take A and then multiply with B, C, D. So basically, you take the product of BCD, or you can take the product of BC and its product you multiply with the D. Whatever comes out, you multiply with A, will give the same answer. So any combination will give the same answer. So I can say A into B, C, D, or ABC into D. So any combination is possible. All are same. So in any group, this associative law is valid. And the last one is each element has its own inverse. Each element in a group has its own inverse. Inverse here means the reciprocal of it. For example, if you have so inverse exists. Meaning if you have C3, it will be having C3 inverse. So forward and then reverse. But if you say sigma V is there, sigma V prime is there, then sigma V prime, negative prime, let's say, is also exist. Just inverse of the process, whatever you do. The reciprocal property also exists in a group. So these are the four properties. So what elements can be present in a group means it has to obey all these four properties. Then we say this is the element of the group. Otherwise, we don't say that. Abelian have told Let me see any other example. Okay, so you are convinced with these definitions. So, are you convinced with this associative law? Anyone have any question?
Sir, can you give an example of associative law?
Yeah, I can give. Okay. Let's take with just C2B itself. Okay. So C2B has E, C2, sigma V prime, right? So take the product of all four. Why not? Let's take E into C2, sigma V into sigma V prime. So you tell me what you will get. You get C2 here, and then sigma V into sigma V prime. From the multiplication table, what do you get? Sigma V into sigma V prime.
C2.
Yeah, anybody? Sigma V into sigma V prime.
C2.
C2. So C2 into C2 is E, right? So this is this combination. If you combine, say E into why not E? We'll just take this one. E into C2 sigma V by sigma V prime. You do this, so if it performs this C2 into sigma V into sigma V prime. So C2 into sigma V, what?
Sigma V prime.
Sigma V prime. So I take product of sigma V prime to sigma V prime. Again, it is going to be E. Okay. So you get both the same. Either way, if you multiply it, it results in E. So like this, you can cross verify with any other group. So associative law should be valid in this case. Then only the element can be present in that group. Okay. So these are the four properties of a group. We'll see, maybe not today, maybe next class, there's something called subgroup. Before that, we study what is called class also. So for studying those things, matrix is important. So all these operations, one can write in terms of a matrix form. So matrix representation. We just see about the matrix representation. Let me start. There are two ways of writing.
Sir,
Yeah.
sir, I want to ask a question that the inverse is defined for a symmetry element or a symmetry operation.
It's a symmetry element.
So what will be the inverse of C3? What do you mean by C3 inverse?
C3 means C3. It has inverse means C3 inverse. Okay.
So how can we use this C3 inverse?
No, it's basically coming back. So you rotate it, no? So if you rotate this one, what happens? Maybe C3.
But the C3 inverse is never present in any group.
It may not be present. It is not represented. It is not given in the group. But it is every element has its own inverse, so we don't write it that in the character table or in its it's a group.
So I think this inverse is defined for an operation.
Inverse is maybe you're right, but
Because
inverse,
if we take C3-1, its inverse will be C3-2, and both of them are present in a group.
you're saying it's an operation. That's what you're saying, right?
Yes, yes, sir. Yes, sir.
Might be true.
According to me, according to me.
Yeah,
So,
might be true. Fine. Okay. It could be operation. Yes. Yeah. C3 inverse is the operation. Fine. Agree with that. But let me finish. C3 to perform. So A goes here, B comes here, C comes here, and then the inverse. If you just perform C3 inverse, it's operation. You rotate in a, so this is clockwise rotation, and then this is anti-clockwise rotation. So we just come back to its original place. So that's the operation. Okay. So it's the inverse of whatever operation you perform. Okay. So yes.
so C3 inverse and C3-2 both are same now.
Yeah, both are same. Yes.
No, these are different. I think.
Three and equivalent as.
That was why I was asking about the difference between operation and element, because that will be the defined in terms of operations.
C32 is twice, right? Let me check. C32 is 2 times rotate.
Yes, sir. That will be different from C3 inverse.
Okay, this may not be right answer. Yes, yeah. C3 twice. So if you rotate it twice, what happens? So C comes here, A comes here, HB. Okay, so this is from C3 inverse means from your original structure, starting geometry, you have to go 120 degrees minus. Yeah, so not from after going 120, not coming back. It is just from starting geometry. You go by 120 degrees left. If you rotate, say just going 120 degrees minus. So if you rotate it, what do you get? Anti-clockwise you rotate, so you get this structure. HB, so C goes here, HA comes here, and HB goes to this place. So this will come like this. So C3 inverse is equivalent to C2, C3 twice. Is it correct? Am I confusing you?
Sir, I think.
C3 is going forward. C32 is 2 times you rotate it. So you end up with C3 once, and then again C3. You brought it here. But that is equivalent to C3 minus. C3 minus means from the starting geometry, you go back 120 degrees. You just rotate in anti-clockwise 120 degrees. That is equal to C3 twice. Okay. But that is in C3. But Sigma planes has, I mean, just the forward and reverse, right? I mean, just place a mirror, again one more mirror you place it. So that's inverse. So for sigmas, it's not going to change much. But for C3, it is C32 is equivalent to C3 minus 1. I hope it is clear now. See, matrix representation will just start. So all these operations, matrix representation of symmetry operations. Okay, there are two ways. Say you when I build a molecule, you can place it on a Cartesian coordinate, or of course in one coordinate. You can rotate the coordinate, or you can follow the atom position. So based on that, you can build the matrix. For example, say you have a point somewhere here. We call it as point P in 3 coordinates. Say this is X, this is Y, and say this is z coordinate. Okay, say so you can represent this point by xyz, right? This is x, y, z. The point P can be represented by coordinate x, y, z. So if you perform certain operation, this point position is going to change. Position of this point P is going to change. So the coordinates also going to change. Okay, so if it changes, how the matrix can be used to represent, to identify that. Let's start with one simple example. Let's maybe use it. If you use the identity element, you're not going to change anything. It's going to stay as such. Say you're not performing any operation, but still this point is going to remain as such. I call that one as say x, y, z. Say 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is x prime, y prime, z prime. So this is for identity operation E. So when you perform an identity operation E, so what is we are doing? We are not going to do anything. So the point will remain as such. To represent that, we'll write in terms of a matrix elements 1, 0, 0, 0, 1, 0, 0, 0, 1, and this is the original position. And after this operation, what is the next position is written here. So this matrix is basically for E operation. Okay, so this is for the identity element or identity operation. Let's go for the planes. Then it becomes easier. Let's have a plane x sigma x. What do you call? Let's do xz. No, let's try with the yz plane. Let's try with yz plane. Okay, so say I'm just placing a yz plane. Y is towards north, and then z is coming out of the board. So if you place a plane here, this point comes here, right? So p prime. The new p is x prime, y prime, z prime comes here. So what happens is the x is going to come this side, whereas yz is going to remain as such. So if you consider xyz as this is xyz, so x is going to become -1, 0, 0, 0, 1, 0, 0, 0, 0. And this is a new point, x prime. So this is for sigma x, no, not z, yz, yz.
Sir, it should be 001 at the last.
For example, yeah,
So minus.
understood. Yeah, don't have to correct these things. Yes, yeah, 001. Okay, so when you place a mirror through this plane, that can be represented as, say, I'm just keeping it something like this. So I'm just cutting YZ plane, then the axis, the x-axis is going to come to negative of x. So that's why it is -x. Similarly, one can write for what other two modes. So say I'm cutting the molecule through this plane. So let me put a parallel line. This one. So if I cut the molecule through xz axis, this is sigma of xz. If I cut it, then y will change its position. So the x will not change. Y will become -y 0, 1. So this is x, y, z. So matrix representation for a plane cutting through sigma xz plane is this one 1 0 0 0 minus 1 0 0 0 1, and then one more plane, right? So one more plane is the xy plane. To cut it through xy plane. So what happens? Cut through xy plane, the z will become minus z. So I'll write it here. Sigma xy. To do that, 0 0. So this is for sigma xy. So these are the symmetry operations, matrix simulation of symmetry operations. One can write in terms of matrix. So here we are considered that the coordinates are moving. Whether atom, the position is of the molecule or atom is remaining same, only the coordinates are changing its direction. So this was sigma planes. What about the inversion? What happens to these Cartesian coordinates if you invert the molecule or invert these coordinates? How the matrix form will look like?
-1 0 0
Minus
0
1 and
-1
minus
0 and 0 0 -1.
Okay, so everything will be inverse. Huh? So it will be like this. All the positions will be in other way. Like z will become minus z, x will become minus x, y will become minus y. So that's why it is diagonal elements all negative. Okay. So what about the? So this is for so we have seen the matrix representation for the identity element and planes. Sigma 3 planes we have seen. Inverse also this way you can write. What about for the rotation? How the one will look like? Any guess?
Sir, we have to consider the rotation of the Cartesian coordinate.
Yes. I'll give the answer first before I go for this one. Okay. So for the rotation, any line you can say Cn or rotation. It will be written as cos theta sine theta minus sine theta 0 sine theta cos theta. So it will be given something of this form, provided we are rotating the axis, Cartesian axis. Okay. So there are two ways of rotating it. We are considering the rotation of Cartesian axis. For that, rotational matrix is given in terms of cos theta and sin theta. Cos theta minus sin theta 0, sin theta cos theta 0, and whatnot. Okay, how do you get this? Let me derive it. Okay, so say this is point P. Say this is R, an angle alpha. Y, and let's go for Z. So let P be a point, and then R is a vector. So you can write what? You can write x1 as R cos alpha, then y1 as R sin alpha. Okay, so for the given point P, I'm writing x1 in terms of R cos alpha, and then y1 as R sin alpha. Now I rotate now we are considering the rotation, no? So from point P, let us move this point to Q. So this is moved certain angle called as Q, and this is theta. Let us move the point P to point Q by an angle theta. So now the new x will be what? That can be written as x2 as or cos alpha plus theta. So you can expand this. Okay, so y2 as or sine alpha plus theta. Okay. So we know the formula, right? The cos a plus b is cos a cos b plus sine a sine b. That I would write. So x2 is it plus or minus? Cos a plus b. Similarly, expand for let me, yeah, okay, we can do this. Sin a plus b, sin a sin b. Cos a cos b. So cos a, I mean sin a plus b, sin a sin b plus cos a cos b. So I have written this. Let me erase it. Right here. So x2 is
So it should be sin A cos B plus cos A sin B.
this
The
one.
sin A plus B formula.
Oh yeah.
Yes, sir. Yes, sir.
Okay. So x2 is we have x1 as r cos alpha. So x1 into cos theta minus y1 sin theta. So this is x2, y2 is r sin alpha is y1 cos theta plus r sin theta or cos alpha is x1 sin theta. That is equivalent to, I can rewrite this. So y2 is x1 sin theta so this can be written in matrix form, right? I didn't say anything about z. Z will remain as z1 will remain as z2 because point is moving only in xy coordinate. So z1 will become z2. So this is basically so basically you have to add it up with z. So this is 0 times of z1, 0 times of z2, like that. Okay, z2 will be these two will be 0 and plus plus 1 time of z1 will be there. Okay, so this is x1, y1, z1. Okay, so we're just writing in terms of matrix. So I think we got the matrix, I guess, right? For rotational, this one. So one can write it for ammonia molecule or any molecule. We can write what will be the matrix element for considering the Cartesian coordinates as uh, representation. You can say representation or basis. Okay, so this is the matrix representation for rotation. Let's go to few examples. Okay, say for example, if you want to consider for C2, what will be the C2 for, what will the matrix form for C2 rotation? C2 is how much?
-1 0 0.
180 degree. C2 is, for example, water molecule. Say you want to perform C2 operation. C2 means it's 180 degree, right? 360 by 2, so 180. So cos n 180 minus sine 180. So just keep substituting it. Then you get its corresponding value. Yeah. For example, C2 means theta is 180. So if you substitute what? Cos 180 is how much? Cos 0 is how much?
Cos 0 is 1, cos 180 is 1.
Cos 180 minus 1.
Sine 0 is 0. Okay. So cos 180 should be minus 1.
Minus 1.
So sine 180 is what?
0.
0.
Yeah. 0. Huh? Sine 0 and sine 180 are 0. So here is 0. So this is for C2. So like that you can write the matrix elements or matrix form of the symmetry operation. Okay. This is for considering the the vectors as basis. You can change the basis also. So that will have different matrix form. Okay, so far so good. You can follow?
Yes, sir.
Yes, all of you, yes?
Yes, sir.
Let me finish it with a few more matrices. Okay, let's start afresh. So let's take, say if the molecule is planar now, so you don't have to go for the 3 by 3 matrix. Simply 2 by 2 matrix is also sufficient. Let's consider water molecule. H. So this is well known to C2V, right? The point group is C2V. We already returned E. E has, so it can be 1 0 0 1. So the molecule is just in a plane. You don't need to consider the third axis. Simply 2 axes is sufficient. So let me consider on the plane for a given this one. So this is x y. So this basis we are considering. For this, the matrix representation is 1 0 C2. Let's do for C2. If you rotate C2, what happens? So if you rotate it, if I'm just considering the y-axis, changing its orientation, it becomes what? Y becomes minus y. X will become
-x.
X will remain as such. Okay, so this 1 0 0 minus 1 sigma v prime sigma v double prime. So sigma v prime is, say I'm just bisecting the molecule into 2. So that is We're just considering bisecting. So if you do that, again x remain as such, y goes to minus y. And sigma v double prime is we are placing on this molecule the plane, so nothing is going to change. So we can say 1 0 0 1. Okay, so one can write matrix representation based on our representation. We are just considering here only the axis, x and y axis. Z we do not consider. So for that, it's just 2 by 2 matrix. And then
So,
based on this, you can build the matrix multiplication.
so how can we differentiate between C2 and sigma V prime if we write 2 by 2 matrix?
Can you please repeat C2 what? C2?
C2 and sigma V prime,
How we are getting it?
because C2 passes through Z axis only. So X should also change in C2.
No, C2 I'm rotating in this direction.
Because water is not a planar, it's pyramidal in structure. No?
So basically, I'm rotating this way. X is remaining as such, x only. Only y is going to minus y.
But it's pyramidal in structure, not in planar.
What is not plane? It's x and y are in the plane. So I'm just rotating the molecule by 180 degrees. So if you rotate it, x will remain as such, and then y will come to other side. Maybe I wrote x. I wrote it something like this. I should have written somewhere here.
But coordinate of H also inverses, no? Reverses.
X is not inversing. No. Say this is y. For this representation. So what x is going vertically, maybe going north, and then y is east side. I mean towards right side. So if you perform C2, what happens? If you rotate it by C2, so what happens? Just y will become minus y, and then x will remain as plus y, plus x1. So something like this you get. Problem?
Yes, sir.
Sir, just by seeing the matrix, sir,
Actually,
so just by seeing the matrix, how will we know that which corresponds to C2 and which corresponds to sigma V prime?
because
Yes, that we can tell. So this is x.
because in water molecule C2 is also a Z axis.
Tell sigma v prime. No, that could be possibility. That could be same type of matrix elements. But
That in BC3 molecule,
that.
water is not a planar molecule.
Can you repeat? I mean, when you speak now, the voice is not clear. It's
I think
noise.
I think two-dimensional matrix we can use in BCl3 molecule, but not in water molecule as it is not planar. It's pyramidal in structure. Maybe I think.
Sir, you're muted.
Okay, so water is planar only. Okay. I just muted it and speaking. So actually, this water is a planar only. So 2 by 2 matrix is sufficient for any planar molecule. Someone asked, how do we know? I mean, sigma v prime and C2 operations, their matrix representation could be the same type. But only thing its property has to be valid. The group property has to be valid. Like if you take the product, it should give another matrix of same of matrix element of that. So let me check one example. I'll take one more example. Say if you take C2 and sigma v prime, or just C2 sigma v, say double prime, you take the product. Okay. So if you do that, C2 is 1, 0, 0 minus 1, and then now double prime is 1, 0, 0, 1. So if you take the product 1 to 1, 1. This is the 0, this is the 0, 0, 0, 0 to 0, this is 0. So this is minus 1. So this is, I'm getting product of these two, C2 and sigma double prime as 1, 0, 0, minus 1. So this I'm calling as sigma B prime. In the matrix multiplication table, can you check it? What is the product of C2 sigma double prime? Someone who have already done this. No, we have already done this. So just check it. C2 and sigma V double prime as it comes sigma V prime. So we can verify it. Whatever you have done in the matrix multiplication, no, the group multiplication table. So this with these 4 matrices, you can verify it. It should be matching. You agree?
So can we get the same results by using 3 by 3 matrix?
Which matrix? C?
3 cross 3.
3 cross 3. Yes, you will get it. Same thing, you will get it.
Okay.
X-axis also. Any representation, you can write X, Y, Z and build up again freshly. That's a unique thing, you know. So if you do that, so this is going to be 1, 0, 0, 0. If you perform C2, what happens? So the X and X will become minus 1, 0, 0, 0. Y is going to remain same. Z will become minus. Sigma V, I'm just bisecting it. So Z and Y, it's not going to change. And then sigma double prime, it's we are placing on the plane. So what happens? Just Z is becoming minus Z. So you get this now. So this is sigma V double prime. Now let's take the product. C2 sigma V double prime. So take the product. The double product is 1. How do we do that? So you should get this one. This into this, minus, minus, plus. So this into this into this, so on. So you get this one. So this might be fine. Okay, so you get the same matrix. This is equal to sigma V prime. So any coordinate, even if you change it, x, y, z, you can replace it by y, x, z, whatever form, but you write it in terms of a matrix form by performing these operations. And then you take combinations, then it should result in same. Okay, so any combination you can try. Like you can check it with the multiplication table. So it will result in same type of matrix. So it could be matrix dimension, could be anything. Like it could be 2-dimension, 3-dimension. It could be say if the molecule has say a benzene molecule. So you have 6 pi orbitals, right? So you can consider that as a representation, and then write 6 by 6 matrix, and then write it. How the matrix changes, one can write it. Otherwise, say there is cyclobutadiene, 4 orbitals, right? So you can represent the 4 pi orbitals as 4 by 4 matrix by various rotation, how that changes by various planes, how the matrix changes. That can be represented. Matrix dimension could be of any type, but once you write it in terms of matrix representation, if you perform these operations, like if product taking product, the 4 properties which I was telling you should be valid. If there is some mistake somewhere, then that property may not satisfy. It will just fail. Okay. Fine. So I think, yeah, you read it. There are books available, online materials are all available. Read it. I'll also maybe during this weekend, I'll send more material. You can go through it. With this background, we'll just build what is class, what is subgroups. Then this matrix are important because we study what is called as reducible representation and irreducible representation. From this matrix, from higher dimension matrix, we bring it down to the lower dimension by certain property. There's something called similarity transformation. So we just reduce it. Okay. So we'll talk about this more in next class. So shall I stop it? So I stop the recording.